We can calculate inverse functions just as we can calculate the inverse of numbers or fractions. As you remember, calculating the inverse of a fraction would be the reciprocal. So, for example, the inverse or reciprocal of 2/3 is 3/2. What happens when we multiply those two is that we get a value that is equal to 1. We can also calculate the inverse of a single natural number. The inverse of 2 would be -2. When I add those two values together, I get a result of 0. We will determine what the inverse of two functions look like on a graph and also algebraically in this video. To calculate the inverse of a function, we are going to switch around the x and y terms and then solve that function back out for y. The notation for an inverse function is shown in the highlighted yellow with a -1 above the f value of the function name. Remember that functions can be named anything we choose. Typically we choose an f or a g or h, but it does not have to be. So in this first example of calculating the inverse, first we are going to switch around the x and y values. Remember that f of x is function notation, which this really is saying y equals the quotient of the quantity of 2x minus 3 divided by the quantity of x plus 1. So I'm going to switch around all of my x and y terms. So to find the inverse, it is looking like x equals the quantity of 2y minus 3 divided by the quantity of y plus 1. Now I need to solve this back out for y. Right now, first off, I do not like that I have a quotient and a very large fraction. So to undo that, I'm going to multiply both sides by my denominator, which would be y plus 1. Remember, when I manipulate equations, what I do to one side, I must do to the other to keep it balanced. This is the same thing on the numerator as the denominator, so it will cancel out, just like saying 5 over 5 cancels out and turns into 1. I'm also going to distribute this x to this binomial and get a result of xy plus x equals 2y minus 3. My goal is to isolate y, so I'm next going to move all my y terms to one side and everything else to the other. So I'm going to subtract 2y from both sides and also subtract x from both sides. So then I have both my y terms on one side and everything else on the right-hand side. Now I need to get y by itself. Y is in two terms, so to get this y by itself, I'm going to factor it out or divide it out. I can do that because both of these terms share it. So by factoring out a y, I'm left with x minus 2 equals -3 minus x. This would be similar to having a product of 2 times 3 minus 2 times 5. So something like 6 minus 10. They share a common factor of 2, so I can rewrite this in factored form as 2 times the difference of 3 minus 5 by pulling this out of both of these two terms. The resulting terms inside the difference are the factors that result in 6 and -10. So y times x is going to give me this term of xy, and y times -2 is going to give me this term of minus 2y. Why this is beneficial is because then I am able to divide both sides by this binomial of x minus 2, which then isolates my y value. So the inverse of function f is equal to the quotient of the quantity of -3 minus x all over x minus 2. Same process, I'm going to begin by switching around my x and y terms. Remember, f of x is just like y, so that is going to turn into an x term and the cube root of now y minus 2. Before I can isolate y, I need to use some inverse operations. I need to undo the cube root. Undoing a cube root, the inverse operation would be cubing it. What I do to one side, I must do to the other. This will leave me with x cubed equals y minus 2. Because these are inverse operations, they cancel each other out. Cube root and cubing are inverse operations of each other. Then I have just one step left to get y by itself by adding 2 to both sides. So this results in x cubed plus 2 equal to y. So my inverse of function f is equal to x cubed plus 2. We also have a property about inverse functions that states that if they are truly inverses of each other, then their composition of functions are equal to each other. So I can prove that two functions are inverses of each other by showing that the composition of functions are equal to each other. So to prove that f of x and g of x in this example are inverses, I'm going to calculate both f of g of x and g of f of x. Remember, when calculating f of g of x, I'm going to take the g function and I'm going to plug it in as the input into the f function. So I'm going to take all of this function and plug it into my x value on f of x. So I have 3 times the quotient of x minus 2 over 3 plus 2. Since I have the same thing on the numerator as I do the denominator, these 3's are turning into a 1, and 1 times x minus 2 is x minus 2. And then this simplifies all the way down to x. So this is my f of g of x. To calculate my g of f of x, I'm going to take the f function and plug it into the input into the g function. So this will look like 3x plus 2 minus 2 divided by 3. My positive 2 and negative 2 are canceling out, and I am left with 3x divided by 3. My 3 and 3 also cancel out and turn into a 1, so I'm left with just x. So you will see that now our composition of functions are in fact equal to each other, so yes, they are inverses. Another way to determine if they're inverses of each other are just to calculate the inverse. Sometimes one method is quicker than the other, but they both will allow you to decide if they are inverses. So if I would like to calculate the inverse of the f function, which is 3x plus 2, remember f of x is like y, so I'm going to write that as an x term and write my x term as a y term. And then if I solve this out for y, first by using inverse operations, you will see that this is now matching up with my g of x function. So just another way to determine if those two functions truly are inverses of each other. So that is what it means to be an inverse function algebraically. Graphically, inverse functions are reflective about each other along the linear function, specifically the identity function of y equals x. So this is one of the examples of the inverse functions that we just found. And you will notice that the blue and green lines are inverse functions of each other, and they were reflective about that red line, which is the identity function y equals x. So if I would reflect the blue line across the red line, it would match up with the green line and vice versa. That is what it means to be inverse functions graphically. So if we go ahead and graph another one of our inverse functions, so one of our functions being x cubed plus 2, and the other function being the cubed root of x minus 2, you will see that these inverse functions also are reflective of each other about that identity function. So if I take the black function and reflect it across the red identity function line, it will match up with the purple function and vice versa.